One of our last major concept of our course is to kind of dive deeper into that linear relationship we talked about way at the beginning. So we're going to kind of go piece by piece, and then we'll learn a couple other techniques along the way. But we're going to start out with this concept of a slope, and a slope is a rate of change. So if you remember when we went over the linear relationship, we kind of worked with a bank and a checking account in that situation. And so we were getting that simple interest where the interest did not earn interest. It was based off that set amount. So it was increasing by $50 per month. So we're going to tie that idea to this concept of a slope and something that's called a rate of change. So you work with rates a lot. A rate is just some kind of ratio comparing two quantities. So you can think about like a unit rate for an item. What we kind of want to work with is something a little more specific, which is called a rate of change. Okay. And so what this does is it compares the change in one quantity to the change in another. And typically this is going to be in terms of time or distances. That's what we usually refer to rate of change as. But again, these two are very similar to each other. The definition doesn't compare too much. But to give you just kind of an example of a rate of change as something you're used to, if you're doing 65 miles per hour on I-4, what that means is you're going 65 miles for every 1 hour of travel. So in the numerator, this is the change in our distance compared to the change in our time. Okay. So if you think about like the unit price of something, that's not a rate of change because it's a change in price for every one item you buy. So it's not really like a change of items there. So that's why we kind of keep rate of change for that specific unit of when we're dealing with our change in distance or change in time as that denominator. Now, realistically, if you think about driving 65 miles per hour, you can kind of bump this up to see what your change in distance is over 4 hours or over 2 hours. So we really can kind of talk about the same rate of change in a number of different ways, depending on what that denominator we use are. So what we say in the case that if we're kind of working with the same base scenario, we say two quantities are equivalent if they have the same value or are interchangeable. Okay. So let's work with an example kind of with hourly pay or daily pay. Suppose at your job you make $100 a day. If then you're asked how much are you going to make in a 5-day work week? Well, you're making $100 a day. You're working for 5 days. So all we're going to do is multiply the two and you would make $500, assuming taxes haven't been taken out or anything yet. But you would make $500 in a 5-day work week. So if I consider the two rates $100 for 1 day and $500 for 5 days, we would say that these are equivalent because it came from that same base pay. And the way I could actually show this is if I take this larger quantity, which is $500 over 5 days, and I reduce this by taking the top and dividing it by 5 and doing the same thing on the bottom. 500 divided by 5 is 100. And then 5 divided by 5 is 1. So it's exactly the same thing as making $100 for 1 day. So yes, these two are equivalent to each other. And again, you don't really have to actually go through and divide by 5. If you really just take 500 and divide it by 5, you get exactly 100 over 1. So you can see that these two are representing the same thing. So something that's super nice about our rates and rate of change is that we can always scale it up or scale it down to be able to find an equivalent form. And depending on what you need to do, one form might be beneficial over another. So let's try an example. Let's write a fraction equivalent to going 60 miles in 4 hours that has a 1 in the denominator. So if I start with my 60 miles over 4 hours, if I want a 1 in the bottom, really what I can do is just divide these two, because that will get rid of the 4 in the bottom. But again, if you want to think about this as simplifying fractions, take the top, divide it by 4, and the bottom and divide it by 4. 4 divided by 4 gives us 1. So 60 divided by 4 gives us 15 in the top, and then 4 divided by 4 gives us a 1 in the bottom. Okay? So going 60 miles in 4 hours is equivalent to going 15 miles in 1 hour. So when we have something like this where there's a 1 in the denominator, we end up actually calling it a unit rate. The reason these unit rates are so beneficial is because this is much easier to then scale up and scale down. Because if I started with this and I asked how many miles would you go in 9 hours, it would be really hard to figure out what I would need to multiply the bottom by to make it a 9. It's not so obvious. Where in this other case, to make a 9 down here, all I would need to do is multiply it by 9, which means you would do the same thing in the numerator. So I could easily scale this up from here. So these unit rates are really valuable because it gives us a very good way to scale up and scale down. And it also gives us a really easy way to compare quantities. So if you think about if you go to a grocery store and you look at like a bottle of ketchup, there's a ton of different sizes and a ton of different brands. And so some of them are going to be a better deal than others. So if you've ever paid close attention to the little tag that's there, it gives you a rate for each ounce or whatever it happens to be. If you're buying like garbage bags, it tells you the price per garbage bag. Those are all unit rates because it's telling you how much it is for one of those items. And the reason that's beneficial is because you can find the better bargain as a result. So you can figure out which ketchup bottle is going to cost you cheapest per ounce that you're buying it. So let's take a look at an example of this. You paid $13.46 for a 3.47 bag of candy at Target. The following week, you then paid $18.75 for a 5.15 pound bag of candy at Publix. We're going to find the unit price for each bag, and then we're going to figure out which has the better deal. And any rounding, we're going to round to the nearest cent since we're dealing with money. Because right now, I have no idea how to compare these particular prices. So we've got different sized bags of candy. Even though it's the same type of candy, I don't know which one was my better purchase. So what I'm going to do is I'm going to figure out what was the price per pound that I paid. So we're going to start with our Target bag. If I think about this as a rate, we paid $13.46 for 3.47 pounds of candy. So what I'm going to do is see how much did I pay for a single pound to get a unit rate on this. So again, all I want to do is I want to get a 1 in the denominator. So really you just need to take the 13.46 and divide it by 3.47. Or again, you can think of this as take the top and bottom and divide it by 3.47. So you might have to round for this, but if you do, when you go through and do this, 13.46 divided by 3.47 is roughly $3.88. And that leaves us with 1 pound in the denominator. Okay. Now I'm going to do exactly the same thing for Publix to be able to get my comparison. So at Publix, we paid $18.75 for 5.15 pounds of candy. So again, I'm just going to do the division. We divide by the quantity in the bottom. And if you take 18.75 and divide it by 5.15, you're going to see it's about $3.64 for 1 pound of candy. Okay. So now, because I'm looking at a single pound for each of these, I can see, based on our prices, I paid less at Publix than I did at Target for a single pound of candy. So this one is going to be my better deal. Okay. So you got to be careful about which ones you put in the top and bottom. If you went ahead and did this route instead, you put the 3.47 pounds for $13.46 in the bottom. You're going to kind of end up with something that's a little bit backwards. So you would be able to see how much candy you got for $1 to make it that unit rate. And then you're going to have to pick out which one gave you more candy for each dollar that you paid. So it's still going to work, but this one's going to make a lot more sense for us. Typically, we like to put prices in the top and then whatever it is we're dealing with in the bottom. In the same way, when we're talking about rates of change, we usually put time in the denominator. What was our distance we changed over the amount of time? Okay. So we've really already talked about linear relationships in this course, and we did it in the terms of that banking account. So we've honestly been working with these rate of changes already. So specifically for a line, when we're talking about the rate of change of something, like the $50 per month we were gaining in interest, the rate of change is more formally called the slope. Okay. And we'll go over the key components of our equation, and we'll talk about a more precise formula for the slope. But we're going to work instead first with a jogger to kind of see if we can figure out what this rate is. How can I figure out this knowing a couple different points on my graph, what's going on? So if you think about someone who's a very experienced runner, they're going to be able to keep a very consistent pace. So they're going to be able to go many miles, keeping a very consistent mileage per hour. So we're going to look at one particular runner, and they can run a single lap around a 400-meter track in 2 minutes. So their pace is going to be 400 meters for every 2 minutes. So what I'm going to start with is I'm going to fill in this table. Based on these times, I want to figure out how far did the runner travel. So starting with 2 minutes, every lap is going to take me 2 minutes. So if my time is 2 minutes, that means this runner has gone 1 lap, which is equivalent to going 400 meters. Okay. After 4 minutes, 2 minutes has passed in that time frame, he was able to do, or they were able to do, another lap. So they were able to go another 400 meters, and after 4 minutes, they've traveled a total distance of 800 meters. And again, 6 minutes is 2 minutes more. So this person is able to run 3 laps in that time frame. So another 400 meters means they've traveled a distance of 1,200. And then you can kind of see a pattern. It happens to be really nice here that we're going up by 2 minutes every single time. So really, we're able to complete 1 more lap each and every way. So this step, 8 minutes, 4 laps, the person's gone 1,600 meters. 10 minutes, they've done 5 laps, which is 2,000 meters. Okay. So they're going to keep going this pace for as long as they possibly can. We're going to now try to answer a couple different questions. So we're going to try to start with what is the runner's rate as a unit rate? So again, unit means that there should be a 1 in the denominator. Okay. So for this, what I want to do is I want to look at the runner's change in their distance over the change in their time. So you could use any of these points that you want. You've gone 2,000 meters in 10 minutes, 1,600 meters in 8 minutes. But you can also just use the information that's at the start. Their pace is they can go 400 meters every 2 minutes. Okay. But again, I want a unit rate. So that means I really want a 1 in the bottom. So I've got to divide this by 2, which means I've got to do the same thing in the top. So going 400 meters in 2 minutes is equivalent to going 200 meters in 1 minute. Okay. So for this next question, it asks us, what is the runner going to cover in 40 minutes? So I'm trying to find the distance. Again, that makes this really nice to use my unit rate because I want their distance over 40 minutes, which means I just need to bump the denominator to 40. So I'm going to start with this unit rate of 200 meters over 1 minute. And to get a 40, all I need to do is multiply by 40. So if I do that in the top, I've also got to do that in the denominator. And so we've got what we need in the bottom, 40 minutes. And if you do 200 times 40, you're going to see that's 8,000. Okay. So this runner would cover 8,000 meters in 40 minutes. So that is exactly the distance that we're looking for. They would cover 8,000 meters in 40 minutes. Okay. So you can see why this unit rate was much easier to do here, because it's not always so obvious what I would need to multiply the denominator by to get to 40. Or if I was covering 45 minutes, what do you need to multiply 2 by to get to 45? I don't know that so easily off the top of my head, but since this is a 1 in the bottom, to get to 45, I just multiply by 45. So it's more straightforward using the unit rate, okay? Now what I'm going to do for this next one is I want to kind of see, is there a connection between these points, which are times and distances, to this unit rate that this runner is covering. So what I'm going to do is I'm going to take the difference in any two distances and I'm going to divide it by the difference in times. So I'm going to look at the change in distance over the change in times, and I'm going to figure out what quantity do I end up getting. So to start, I'm going to work with using 4 and 800 and 6 and 1200. We're going to use these pieces of information. And then I'll also show you if I pick two different ones, we still get the same thing. So I'm going to look at the change in the distance divided by the change in the time. Okay. And the piece of information that I'm using is we've gone for 4 minutes, we'll go 800 meters. And then for 6 minutes, the person can go 1,200 meters. So if I think about my change in my distance, we do one minus the other. So I'm going to kind of do it piece by piece. If I take 1,200 meters and divide it by, or subtract 800 meters, the distance they will have traveled is 400 meters. And then I'm going to go ahead and I'm going to divide this by the change in their time. And I'm going to stay consistent. I started with 1,200, subtracted 800. We want to do the same order for the time. So we want to do 6 minus 4. So this person ran an extra 400 meters in 2 minutes, which is exactly that runner's rate. So you can even condense it down to the unit rate, 200 meters for every 1 minute. Okay. So by looking at this, we ended up with the runner's rate. Okay. If I go back up here and I pick two completely different points and I do the same thing, I'm going to get the same answer. So let's instead do 4 and 800 and 10 and 2,000. So if I pick these particular points, and again, I'll just write them off to the side, 4 and 800, and 10 and 2,000. And I look at the change in distance over the change in the time. I'm going to start with the bigger number, so 2,000 minus 800 meters. And then our change in time, again, we're going to stay consistent. 2,010 pair up, so I put the 10 first, and then the 804 pair up. So 2,000 minus 800 means the runner ran 1,200 meters over a total time of 6 minutes. And again, if I make this a unit rate, that means I'm going to take both top and bottom and divide it by 6. You still end up with 200 meters every 1 minute. Okay. So this is exactly our slope. It is just the runner's rate of change. They are going 200 meters every 1 minute. That is my slope for this linear line. And the way I also know to kind of foreshadow into some other stuff that we're going to do is you see how this time is increasing by 2 each and every time. You've got that consistent change. So there's a consistent change in the y value as well. So this is really exactly how we find our slope. It's going to be a formula very similar to this that just calculates the change in one value over the change in the other. In the numerator, it's the change in the dependent or y variable. In the denominator, it's the change in our independent or x variable. So let's look at how we calculate the slope of a line. So again, if we have a linear equation that's just a straight line, let's say it has points x1, y1, and points x2, y2. When I go to calculate the slope, it's usually denoted by a variable m. What we're going to do is we're going to take the change in our y values and we're going to divide it by the change in the x. Okay? So all we do is subtract the y values, subtract the x values. The key is, though, you have to be consistent. So looking at my particular picture I have, I'm going to take one y value and subtract the other. So we're going to do y2 minus y1. Okay? And I just need to be consistent because I picked y2 first for the y's. When I go to do the difference in the x values, I want to stay consistent. So I'm going to pick the same x value from my y2 coordinate. So we have y2 minus y1 over x2 minus x1. So the first comes from the same point, and the second also comes from the same point. Okay. There is another way you can also think of this. So we like to call this another thing as well. If I go ahead and draw a straight line over and a straight line down, that creates that right triangle. So this distance we're running straight across in the x direction is called our run. And the distance we're changing vertically, which is the y values, is the rise. So you can also think of this as the rise over the run. How much your y is changing versus how much your x is changing. Your slope can also be negative if your graph is going this way because your run is, or your rise is negative. Okay. So going back to all of the pieces of our line, if you remember, lines have a very particular equation. Our output is equal to some initial value or initial amount plus that rate of change multiplied by your input. Okay. So in terms of the banking, it was the amount we invested multiplied by the rate we were increasing by each times, multiplied by the number of months. It's just a more general formula here. So we have variables for each of these. We know our output value is y. Our rate of change is what we're calling the slope, that's m. And our input value is typically x. Okay? So this value here, this rate of change, is exactly the slope. This initial value is the amount we're starting with. This is going to be denoted by b. And what that actually is it's where you're beginning on the y-axis. This is our y-intercept. Okay. And we'll talk more about how to find that here, but this again is if you have none of your input, what are you starting with for your output? So more commonly, the way you're going to see these lines written is your y equals mx plus b. Okay. So let's try a couple examples. We're going to start by finding the slope of the line passing through the 2 points. We've got negative 5, 3 and 7, 9. And I'm going to do this 2 ways because it really makes no difference which one you put first. Typically what happens is you see this first point and you call this one immediately x1, y1. And then the second point is x2, y2. Just seems the most natural. This first one's first point, second one's second point. So our slope is the difference in y values divided by the difference in x values. And again, just staying consistent. x2, y2 is a point, and these two come from a single point. So filling that in, the way I kind of like to go through the slope is I start it by setting it up. We've got division, we've got 2 minus signs. I'll fill in 1 point. The y value is 9. The corresponding x value is 7. So I'm filling in that full pair in that first spot from that 1 point. Then I'll go in and use the other point and fill it in the second spot. So we have to subtract the y value 3, and then we have to subtract the x value, which means we're subtracting negative 5. Okay. 9 minus 3 gives us 6. And then 7 minus 5 is really 7 plus 5, so the denominator is 12. So our slope is 6 over 12, which does simplify. Top and bottom can both be divided by 6. So it simplifies to 1/2. Okay. If you wanted to do it the other way, you absolutely can. It does not matter which point you pick to be in the first spot. So I'm going to show you just by switching this around. Okay. Maybe I go ahead, my first point I'm going to put in the first spot because that just made the most sense to me. The y value is 3. The x value is negative 5. Then we put the other point in the other position. So the y value for that second point is 9. The x value is 7. If you do 3 minus 9, that gives you negative 6. Negative 5 minus 7 is negative 12. A minus divided by a minus turns positive. So it's 6 over 12 or 1/2. You end up with exactly the same answer. So again, it makes 0 difference which point you pick to be x1, y1 and which point you pick to be x2, y2. You will end up with exactly the same slope every single time. Okay? So let's just try one more. Jose buys cheese from the farmer's market. We want to figure out how much does the cheese increase for each ounce he buys. And then we're also going to figure out what is the slope of the line. So just kind of approaching this again from looking at the graph, If I want to know how much the cheese increases for each ounce he buys, if I look at the 1 ounce, it's going to cost Jose 66 cents for that 1 ounce of cheese. So this is exactly how much the cost increases for every 1 ounce. Okay. So that was easy to dissect just from the graph itself. Now, if I want to find the slope of the line, I'm going to just pick any of these 2 points. So I'm going to go ahead and pick this one, 166, and then the one right after that, 132. But again, you can pick whichever 2 points that you want. So if I go to find the slope, m, we go ahead and just set up our fraction with subtraction. Starting with this point, our y value is 132, and the x value is 2. Then going on to this point, the y value is 66, the x value is 1. If you do 132 minus 66, you get 66. And then 2 minus 1 is 1. So you really end up with exactly that unit rate that he's paying for the cheese. Okay. If you pick 2 different points, you'd end up with exactly the same thing. And then to also just kind of foreshadow, if you look at this graph, it also goes through 0, 0. You buy no ounces of cheese, it costs you no money. So in this case, your value of b for your y-intercept is 0. So the equation for this, we could set up y equals mx plus b. Our y and x are variables. The slope is 66. And then our value of b is 0 because no cheese costs no money. So that would give us the equation of the line. And again, this is going to be what we kind of end with throughout the semester. We're going to go through if I have points or if I have the slope, if I have all these different components, how can I come up with this equation y equals mx plus b to represent the situation? Because this works a little bit nicer. If I now buy 10 ounces of cheese, I just go ahead and plug in x is 10. And I would do 66 times 10 to find my amount of cheese. And that's much nicer for weird values because if I buy 10.17 ounces of cheese, using the graph, I can't figure that out, but I can use that equation to get the exact amount I would pay. So building these equations is going to be super essential to a lot of stuff that we do.